welcome to this introductory offering of our course, The Mathematics of Waves. This is the 6th lecture and the last lecture for this week on oscillators. Now, in our previous lecture, that's lecture 5, 1.5, we talked about the impulse response of a system that is described by an equation of this form. And we took a general form, put in a phase factor, which we so far haven't really used much, but we wanted to have a general formulation that we could use in future. And what we showed was that for an impulse response, you have these 4 components, H11, 12, 21, and 22, and they all have the form of these damped exponentials. And where does this damped exponential come from? Well, when you look at the eigenvalues of this matrix, they are complex numbers with a negative real part and this plus minus j omega, right? So that's the j omega is what gives you the oscillations, and then there's the real part which damps it. Now, what we want to do in this lecture is talk about sinusoidal excitation. So the source term, instead of looking like a number times a delta function, we now have a number times a cosine function with some typical frequency omega, some source frequency omega. And the response is now what we're writing as x1 omega and x2 omega. Now, just as we had this impulse response H matrix, H11, H12, H21, and H22, now you could define a R11, R12, R21, and R22, something that relates the amplitudes of these sources, S1 and S2, to the actual response that you get. And last lecture, we already found this H matrix. Our job now is to find the R matrix. Of course, you could solve it numerically. The way you do it is you can have shown the solution for a particular choice of parameters. And the code is very similar, except that now the source term is set to be a cosine omega t, as opposed to that impulse function that we are using before. But otherwise, much the same code. And if you run it, what you'll see is that the response, if you have a cosine omega t at the input, the response will also look like a cosine or a sine with the same frequency. But you'll see that it gradually builds up to some value and then reaches a steady state. So this is if your source frequency actually matches the resonance frequency of the system, the one that's in your original equation. If they match, that's like what you call the resonant excitation, then the system builds up and you have a large response. Whereas if you are off resonance, like if it's a 90% of the resonance frequency, then you'll find it cannot build up very well. Okay, you see some beats for a while, but then it doesn't build to as large a value. And this is what you know in general. When you, I guess, when you're trying to help a kid on a swing, you want to push with just the right frequency. And if you do that, then the swing will gradually build up. But if you push with the wrong frequency, then I guess you'll be getting in the way. So that's basically what this math kind of shows, that when you push correctly, you get a nice build-up. Now, one thing we're interested in then is that, well, what is the steady state amplitude as a function of this source frequency? So if I sweep this small omega, what will I see? So what we could do is, again, use the numerical code and use a particular source frequency omega, look at this Rij, and then record its maximum value. And what we'll find is this nice sharply peaked response, that when your omega actually matches omega R, that's when you get a nice peak in the response. But then as you go off resonance, it dies out, falls off. That's what you see. Now, what we want to do then is get an analytical expression for this. And we can make use of the impulse response that we have already found by remembering that, once you have an impulse response for any source function, you can always do this integral. This whole idea that if I want the response at a time t, then I have to look for what the source was at time t prime, and then multiply it with what I'd get from the impulse response when at t, if you have hit it at t prime. So cosine omega t prime tells you the impulse that hit it at t prime, because any source, you could think of it as a sequence of impulses. So what you had at t prime, and h tells you the response you get at t because you hit it at t prime. And then you have to integrate it over all t prime. This is exactly what we had done back in lecture 1.2, I believe. Now, it is convenient here, though, to transform variables a little bit. That is, instead of this t prime, call that t minus t prime. So in other words, previously the idea was I'm interested at time t, and t prime is the time when the source was active. And then I have to add up over all t prime. But right now, the transformation kind of takes the t prime and replaces it with t minus t prime. So what t prime represents is the time interval between my observation and the source, and when the source was active. But mathematically, this is just a change in variables. What used to be t minus t prime has become t prime, and so what used to be t prime has become t minus t prime. And you'll notice, so those two are mathematically equivalent. Now what we do is, we notice that this cosine a minus b is this cosine a cosine b plus sine a sine b. And so this integral can be separated into two parts. You have a part that's times cosine omega t and a part that's sine omega t. So in other words, the response, if the source was cosine omega t, the response will have a cosine component and a sine component. And the amplitude of the cosine component can be obtained from this integral, which is this cosine omega t prime times the impulse response. And the sine component, you'll have the sine omega t prime times the impulse response integrated. That's it. So to go further then, I need to get these impulse responses from the last lecture, which I've written down here. And you remember, the black items on the right, those are the important terms. And then there is the small correction in blue when alpha L is not equal to alpha S. Not very important for most parameters we're interested in, but I've written the full form here. And what we need to do is substitute these back into these integrals and then do the integral. And that's what we'll be doing for the next few slides, which will be a little bit tedious algebraically. Please bear with me. So the thing is that when I substitute this in here, you can imagine you'll get into products that look like this. Cosine omega t prime, cosine omega r prime t prime. Right? This comes from the impulse response, this comes from that source term, and you have to do that and you have to do the integral. And what is convenient is to take this product of cosines and write it as a sum of two cosines. One of them is the sum term and the other is the difference term. Same with the sine, product of sines, sine cosine, cosine sine. They can all be written in terms of a sum frequency and a difference frequency. And then you see I have to do the integrals for each of these terms individually. And that I can do making use of this rule for the integrals, which is that when you take e to the power minus alpha t prime, multiply with cosine and integrate it, you get this function, which I'll call the c. And it depends on this frequency omega 0. And then with the sine, I get this function, which I'll call S. And since every term is like either a cosine or a sine multiplying an exponential, when I use those integrals, I can write down the answers using those integrals. Now, but before I go on, let me just point to one little subtle thing I did here, which is I changed this upper limit to infinity. And that's because we are kind of interested in the asymptotic response. That is, you see, you're exciting it with a certain frequency, and what will happen is it will gradually build up. You know, the way a swing gradually builds up as you push. And the initial part of the build-up, we don't really care for. What we want to know is, after it has had enough time to build up, what do we get? Okay? And so, to get that limit, I can do this, extend this integral to infinity. And actually, once this limit is large, so large that e to the power minus alpha t is 0, and it's very small, it really doesn't matter how big it is. Anyway, so for this purpose, we just set it to infinity, and using it, you'll get expressions like this. For if you want the R11, the cosine amplitude, you'll get this C omega plus omega r prime plus C omega minus omega r prime. So in each case, whether it's R11 or R22 or R12 or R21, the point is you'll get these two terms, one of which will be the sum frequency and the other will be the difference frequency. And this is where, by the way, when I'm writing these expressions, I've ignored these corrections due to the blue terms. And as we had discussed, that's usually a small correction. We could include it, but just messes up the algebra a lot. So I've left that out. Now, remember, these functions S and C, they're all very sharply peaked functions. In other words, they are non-zero only for a small region around the point where omega 0 is equal to 0. You see? So in other words, these functions are significant only when the argument is 0. And the point is the sum frequency, of course, will never be 0, because the way we're doing it, omega and omega r prime are both positive numbers. So when you add them, you'll never be 0. So you are always asking for the value of these C and S functions at far from this region of interest, somewhere out here. So what you can do then is ignore that sum frequency term. And so the dominant term is really the difference one, which is exactly 0 when your driving frequency omega matches the resonant frequency omega r prime. And so that gives you the response. And so what you then have is what I have stated here, that R11, R22, R21, and R12, depending on the C or S functions. And the C function looks like this peak, whereas S kind of looks like this double peak, a negative and a positive peak. Right? So sometimes it's the S function, it's important. And these then give you the coefficients of the response. Remember, we are hitting it with a cosine, but the response that we get at steady state has a cosine component and a sine component. And what these give you is the coefficients of the cosine component and the sine component. Now, what we want to do is apply what we just did to a concrete physical system. You see, where we'll consider an RLC circuit, you know, the type we had discussed before, except that previously we didn't have these resistors or this source term IS. So I've kind of added these three things into this story. Previously, we only had an LC circuit driven by a voltage source. But now I've added a resistor RS here, resistor RL here, and I've also added a current generator here. And what I'll show in the next few slides is that the circuit equations, the equations describing this circuit, have a form like this, which is just like the generic one that we have been talking about in lectures 5 and 6 and this one. So it's exactly the same form. So you can make use of everything we have done, but now we are talking about a specific physical system. So how do you get from this circuit to this equation? Well, the first step is write down the circuit equations. So previously when we talked of LC circuits, that was back in lecture 1.3, we had L di dt equals V minus V. But now you also have to include this I times Rs, because that's the voltage across the resistor. So V minus V is actually L di dt plus IRs. And that's why you have this IRs over here. Similarly, for C dV dt, that's this current into this capacitor, we have the current coming in from this side, but now you also have this V over RL. That's the current flowing into that load resistor, the RL resistor. And then you have this current source, IS. So these three extra terms come in now, whereas what I had done to keep things simple back in lecture 1.3 was the black terms. We didn't have the resistors or the current source. Now I can take that and write it in matrix form. Like di dt is minus Rs over L times I minus 1 over L times V, etc. So this we have done before in lecture 1.3, if you remember, probably 1.4 as well, where we first write down the physical equations and then put it in matrix form. Because once it's in matrix form, then it's easy to relate it to the things we have been talking about. So we get here. Next, what we do is, remember, we have to scale the variables so as to make these off-diagonal terms equal. And the way we do it is, instead of I, we multiply it by IZ0. And that gets a Z0 in here, and also in the denominator in here. And this stuff is exactly like what we had done in lectures 1.3 and 1.4. And then the idea is that you choose this Z0 such that Z0 over L is equal to 1 over Z0C equal to omega R. That's how we get this. Omega R equals square root of 1 over LC. And you get the scaling variable Z0 as square root of L over C. So that's how you get this equation, which you'll notice is looking like our generic equation. Now, specifically what we'll do going forwards in the next couple of slides is we'll consider the case where you have a current source for a generator, but you don't have a voltage source here at all. So I'll put a shorting line here. So there's no voltage source. So what that means in the equation is it takes out this omega V from here. And all we have is a current source. And we'll then assume a cosine driving term, Is cosine omega t. So this is the equation that we want to solve. And earlier in this lecture, we had already worked on an equation that looked exactly like this. And we had shown that in that case, if you want to know the voltage, this voltage here, we have to look at the response function, the R22, because the source term, it's the second source term that's non-zero. And we want to know the response, the second response term. So we need to look at this R22, and omega 0 is, Z0 is is just this amplitude here. So you put that in here. So that then immediately we have the voltage. And remember, for R22 and R22 cosine and R22 sine, we have these functions. One of them is looks like this sharp function here, like a delta function. And the other has these two peaks, something like this. Now, one question you might want to know is, well, how much power is this circuit drawing from the source? And the way you find power is you multiply voltage with current. So that will give you the power. So again, you'll get two terms. There'll be a cosine square omega t and a sine omega t, cosine omega t. And if you time average it, the time average power, cosine square omega t has an average of half, whereas sine times cosine has an average of 0. So the second part, that's what people usually call the reactive power. We don't worry about. But the active power then, cosine square omega t gives you a half. That's what I've put in here. So finally, if you looked at the average power, you'll get this omega z0 over t over 2 is squared times this r22c. That's this cosine response term. What is r22c? Well, that's what we had looked at before. It has the form of this alpha divided by this quantity. And what you can show is that this function, you see, as alpha becomes small, it gets taller and taller because right around the resonance. Because right around the resonance, I can neglect this term. So it is alpha divided by alpha squared, which is 1 over alpha. So the peak value is like 1 over, goes as like 1 over alpha. But the width of this thing goes as alpha. Because the bigger you make alpha, the broader this function looks. And so this function has this property of a delta function, that the area underneath stays constant. So you can show that if you integrate that function over all omega minus omega r prime, if you integrate it, the answer will be pi. So the area stays the same with alpha, but as you reduce alpha, it just gets taller and skinnier, thinner. Whereas if you make alpha bigger, then it will get shorter, but then it will broaden out. So you often write this as a delta function. And so that leads us to this final result, which is that that the time averaged power is this delta function that looks like this, with a factor in front that tells you the strength of the delta function. And I should mention here that the way I'm writing IS, it's like the peak value of the source term. Sometimes people talk in terms of the RMS value. And that RMS value is like 1 over square root of 2 of the peak value. So if you do that, then instead of this pi over 4, you'll have a pi over 2 here. But other than that, that's a minor point I just wanted to mention in case you are used to the RMS result. And note here that what you're writing is the power that this circuit will draw from my source under steady state conditions, that is, in the asymptotic response. That is, in the beginning, the answers will be different, but after it has settled down. And actually, if you just wanted this result, you could have got it relatively simpler in a relatively shorter process if we had used all these ideas of phasor notation that you learn if you have taken courses in AC circuits. But here I didn't want to use any of that, and also wanted to deal with this time dependence explicitly. Even though at the end, of course, we are still extracting the asymptotic response. But what I wanted to generally describe to you is how you can solve these differential equations or use the differential equations to describe the dynamic behavior of all kinds of physical systems. But this then kind of, I guess, finishes what I wanted to cover about oscillators. And the final result that I'll make use of somewhat next week when we talk about waves. Because next week, I'll try to explain how what you've learned from oscillators could be applied to waves. And the one result we'll make use of is this expression for the power that is drawn by an oscillator system from a source term. And that's this result that's out here. Okay. Anyway, so that concludes this week on oscillators, and next week then we'll pick up waves. Thank you.